Hello everyone, thank you for being here. I'm Vanessa Elongo, a PhD candidate in economic geology at the University of Alberta. Today I will be presenting a part of my research on the Canton tungsten deposit. So let's start with why we are interested in tungsten in the first place. So this graph shows the criticality of raw materials defined as a function of the economic importance and supply risk. And we can see here the place of tungsten among the metals with the highest economic importance. So this has been classified for Europe, but it is a global problem except for China, which ranks first in the world in terms of tungsten resources, reserves, and production. In terms of properties, tungsten has the highest melting point of all metals, and it is among the heaviest metals as well. So because of those main properties, tungsten has a wide range of uses, and just to cite a few, it is used to make heavy metal alloys, carbides, cutting and drilling tools. So tungsten is widely used, but its production is very localized, which makes of it a critical metal. The criticality of tungsten is the reason why we are interested in understanding the processes that govern tungsten mineralization. So tungsten is commonly associated with crystal-derived felsic magmas, so usually granitic magmas related with major orogenies. However, the involvement of metal fluids, so mafic in composition, has also been proposed in several tungsten deposits, for example in Iberia, in China, and even in Canada. And that was based on studies using different methods like noble gases, radiogenic isotopes, melt inclusions, whole rock compositions, etc. So this photo here is from Adlaka et al. 2018, and it shows a mafic melt inclusion in apatite from a monzogranite pluton that is associated with the Canton deposit. So the occurrence of mafic melt inclusions and the presence of mafic dikes at Canton and the evidence of other metal-derived fluids in other tungsten deposits led us to think about whether or not additional controls for tungsten fertility include the need for input of a metal-derived mafic magma, or if we only need a tungsten pre-enriched crustal source for the mafic magma, for the felsic magma, sorry. And this is the question we try to answer in this study for the Canton deposit. This map shows a part of the Canadian Cordillera. So here we have the Yukon and a part of the Northwest Territories. And on the upper right corner here, we have the map of Canada showing the location of this portion we are looking at. We have a few tungsten deposits here represented by the red stars. The tungsten deposits that we have here are the only major tungsten deposits in North America. On this map, the dashed lines represent different plutonic suits, so same color means similar age. We have the Tombstone tungsten belt here in green, which comprises mid-Cretaceous plutonic suits that are associated with the tungsten deposit that we have in the Silver Basin, Canton included. So here is a cross-section of the Canton deposit. The mineralization is hosted within two carbonate units, the Swiss cheese limestone here and the O limestone here, and these units are surrounded by argillite units. And those carbonate units have been scarnified at the contact with the mine stock monzogranite pluton and related apletic dikes. The tungsten being mineral at Canton is a calcium tungstate called scheelite. So we have two ore bodies here at Canton. The underground east zone ore body and the surface or near surface pit ore body. So we also have at least one lamprophile dike present at Canton, but it is not shown in this cross-section, and this lamprophile dike is the only potential proxy for metal-derived rocks in the Canton area. So the aim of this study is to determine what are the likely sources of the ore-forming fluids at Canton, and if any particular crystal or metal material contributed mainly to the ore-forming fluids at Canton. So we decided to use the Samarium, Neodymium, and rubidium-strontium isotope systems to achieve this goal. So in the next few slides, I will first discuss how these two isotope systems function and how they can help us in this study. So let's start with the SMND system. So samarium and neodymium, they are both middle rare earth elements. They have a similar charge and radius, and as a result, they have a similar geochemical behavior. Samarium has 7 naturally occurring isotopes, 3 of which are radioactive, but only samarium-147 has a half-life that is sufficiently short to produce small but measurable differences in the abundance of neodymium-143 over periods of several million years. So the abundance of neodymium-143 increases with time by alpha decay of samarium-147. So samarium-147 is the parent isotope and neodymium-143 is the daughter isotope, and this decay provides the basis for the SMND method. The neodymium evolution is described in terms of a model called CHUR, which stands for Convexic Uniform Reservoir. And a general assumption about the Earth is that the crust has been created from the mantle by magmatism. The CHUR model assumes that terrestrial neodymium has evolved from a uniform reservoir with samarium-neodymium ratio was equal to those of the chondritic meteorites. So that reservoir represents the bulk Earth prior to fractionation of the Earth into core, mantle, and crust, postulated here to have occurred about 3 billion years ago. So the isotope signature of the CHUR is the one of the chondritic meteorite. CHUR evolution line is a reference line against which the neodymium ratio in samples are compared. So this graph here represents the evolution of the neodymium composition in individual reservoirs after the decoupling of samarium and neodymium due to partial melting of the mantle. So on this graph, we have the neodymium 143-144 ratio over time. We usually use the epsilon neodymium notation instead of using the neodymium ratio because it is easier to use, and this epsilon neodymium represents the deviation from the CHUR for any sample at any given time, and these deviations are small, so when we write them in deviations in part in 10,000 it is easier. So for the CHUR itself, the epsilon neodymium will be equal to 0 because if we replace sample by CHUR here, we will get 0. So neodymium is more incompatible than samarium. So that's been the case. Partial melting of the mantle will remove neodymium, more neodymium than samarium from the mantle, and this depletes the mantle in the daughter isotope neodymium. That's why we talk about depleted mantle here. So thus, as a melt undergoes fractional crystallization from a mafic to a more felsic composition, the abundance of samarium and neodymium changes, as does the ratio between samarium and neodymium. As a result, mantle-derived magmas have high samarium-neodymium ratios, which will result in positive epsilon neodymium values, and so we have more samarium-147 that can generate more neodymium-143 relative to the original ratio found in the CHUR. On the other hand, crust-derived magmas have low SMND ratios, which will result in negative epsilon neodymium values in the rocks. There is very little SMND fractionation by geological processes other than partial melting of the mantle. So the neodymium isotope ratios in a magma is characteristic of the source region from where the magma was extracted, and the ratio remains unchanged until subsequent mantle partial melting event occurs. So this means that rocks and minerals will have isotopic signatures that reflect their sources. Rocks or minerals derived from any source will naturally have the same neodymium isotope ratios as the one of the source. So now let's move to the RBSR system. Rubidium is an alkaline element and strontium is an alkaline earth element. They also have different charges and radius. which result in different geochemical behaviors. The abundance of strontium-87 increases with time from the decay of rubidium-87, and that provides the basis of the rubidium-strontium method. Similar to neodymium, the evolution of strontium can also be described using the CHUR, and on this graph we have the ratio of interest, which is strontium-87 over strontium-86 versus time. If at any time the metal is partially melted, rubidium and strontium will be fractionated. However, the rubidium-strontium systematics will behave in an opposite manner to the SMND systematics. Rubidium is really incompatible, so during partial melting of the metal, rubidium preferentially stays in the melt and is incorporated into the crust, whereas strontium will be least concentrated in the crust. So in the rubidium-strontium system, the parent isotope is depleted in the metal. The strontium isotope ratio of the metal about 4.6 billion years before present was about 0.699, and since then the strontium isotope ratio of the metal has increased slightly only. However, in the crust, the strontium isotope ratio has increased significantly because we have more rubidium-87 there, which can generate more strontium-87. So, if at any time we compare the strontium isotope ratio of a sample with the strontium isotope ratio of the CHUR, we can get an indication on whether that sample is crust-derived or metal-derived. So the present day strontium isotope ratio of the CHUR is about 0.7045, and the present day value for crust-derived rocks are higher than that, and for metal-derived rocks, they are lower than that. Rocks and minerals will have a strontium isotope signature that reflects their source. So the RBSR system is also a good method for source tracing, but it has a disadvantage compared to the SMNT method because of the mobility of rubidium and strontium. Because of their solubilities, they can be transported by fluids and may be moved into or out of the system, and that is a fact that needs to be considered when using that method. So since both the SMND and RPSR systematics can be used for source tracing, we can use a diagram coupling the two methods. So this graph here is epsilon neodymium versus strontium isotope ratios, and on this graph, the first thing that we need to look at is the CHUR. So the CHUR is here, and after that we can look at our other reservoirs, right? So on this graph, any sample with a positive epsilon neodymium value and the strontium isotope ratio lower than the CHUR will be metal derived, and any sample with a negative epsilon neodymium value and a strontium isotope ratio higher than the CHUR will be crust related. So this graph here is what we will be using in the study to answer our questions. So the aim of this study is to determine what are the likely sources of the ore fluids at contact, and if any particular crystal or mental material contributed mainly to the ore fluid. So analyzing scheelite and all the local rocks, which represent local reservoirs, will allow the tracing of the source of the ore fluids at contact. At the time scheelite crystallized, its neodymium and strontium isotope signatures should have been the same as the signature of the rock or the reservoir from which the ore fluid was sourced. So basically, if the ore fluid is related to a rock in the area, the signature of scheelite will ideally overlap the signature of that rock. So this method will work just fine for us because scheelite can incorporate strontium and rare earth elements. So in this study, whole rock samples representative of all the local lithologies were analyzed. So we analyzed the Manstock granite, Wanapichik dike, the Lemprofire dike, argillite, and unaltered limestones. And we also analyzed scheelites from different skarn faces within the deposit. All the samples were analyzed through one method only for both strontium and neodymium isotopes, which is solution mode inductively coupled plasma mass spectrometry. And in this method, samples are crushed, powdered, dissolved, then the different chemical elements of interest are separated and collected into a solution, which is brought to the mass spectrometer for analysis. So the picture on the left here is just a picture of the lamp sample, and on the right here we have powdered scheelite under a shortwave UV light, so scheelite fluoresces. Now let's finally move to our results. So this graph shows the strontium isotope composition versus neodymium compositions, and the data here have been recalculated for the time scheelite crystallized at Quantum, which was about 95 million years ago. And on this graph, all the black circles here represent scheelite from different scan faces and different shading, and all the squares represent whole rock samples, so different color represent different lithologies. Scheelite data did not yield any specific signature from a scan faces to another one, so that is why we did not differentiate them. So if you remember how this graph works, on this side here we have the mantle area, and on this side we have the continental crust area. And the first thing that we can note here is that all the samples are in this area, so they seem to have derived from a continental crust source. So there was no input from mantle-derived fluids in the ore-forming fluid nor in the outcropping rocks at Quantum. Even the lamp profile dike in green here, which is the rock that was most likely to provide an indication of metal input in the area, has a crystal signature. So for the neodymium isotopes, we can see that the lamp profile here has the highest epsilon neodymium value. It is followed by the Minestock monzogranite and applied dike. Then we have scheelite, limestone, scheelite again, and some argillites with the lowest epsilon neodymium values. So since neodymium has very little mobility, the neodymium signature of scheelite is unlikely to have been picked from the sedimentary country rocks. So the neodymium signature of scheelite here is more likely to represent a mixture between a fluid derived either from the Minestock monzogranite pluton or the apletic dike in orange here, with a fluid derived from another intrusive rock that is not outcropping, that is maybe hidden, and that intrusive rock would need to have an epsilon neodymium signature that is lower than scheelite. So that unknown hidden intrusive will be located somewhere down here, and yes, it will have to have a signature lower than scheelite, so lower than -20. As far as strontium isotopes are concerned, the strontium signature of scheelite here is the same as all the local rocks, at the exception of the argillites here in purple. So the signature might be a mixture between our local intrusive rocks and the inferred hidden intrusive, and in that case, that intrusive would have a strontium signature on this side here, lower than scheelite, which reduces our box to this part here, this part only. So another possible explanation is that the scattered strontium signature of scheelite means that the ore fluid picks some strontium from the surrounding rocks during its ascent. In conclusion, the local and profile dike is unlikely to represent a metal input in the area due to its crystal neodymium and strontium signatures. And two, there is no evidence of metal input at Quantum, so we propose that metal input is not critical to generate tungsten mineralization. And the neodymium and possibly strontium isotopic composition of scheelite suggests that the ore fluid at Quantum were a mixture of fluids derived from the local outcropping intrusive rocks and a hidden intrusion with a lower epsilon neodymium signature. I would like to thank everybody that contributed to this work in